Hi there, thermophiles. So before we move into new content, I thought it would be helpful if I did a quick review video on some of the concepts and equations that we derived in the first part of class. Unlike videos with new content, I'm not gonna tell you to pause and tell you specific activities to do, but I will say I'm going to make jumps from equation to equation, and I'm not going to write out all the steps in this video. So if you aren't sure about how to make those leaps, then I encourage you to pause and try to recapitulate the steps of that derivation. And if you can't recapitulate those steps, that's a great kind of question to bring to office hours. So what I'm going to review in this video is the Stirling cycle and a constant pressure process. We usually start by explaining our processes with a PV diagram. And I almost always think of PV diagrams with a series of isotherms. Maybe a cold isotherm and a hot isotherm. There are a few reasons why PV diagrams are so useful. One, graphs are just good communication. Pressure and volume are often quantities that we can measure. We also have tangible experience with these equations, so I get the sense that you can look at this graph and you can feel an increase in pressure and you can imagine visualizing an increase in volume. The other thing that's nice about these graphs is that the integral under the curve is work, and so by looking at the area under the curve, we have it's a nice way to visualize work. The Stirling cycle, let's say we start at some state 1. The Stirling cycle is broken down into 4 steps. It doesn't actually matter where we start, but there are always 4 steps. So in this case, the first step is going to be isothermal compression to some second volume. Then it's constant volume heating to some third state. Then we do isothermal expansion to a 4th state. And constant volume cooling to get back to our initial state. At the time in class when we introduced the Stirling cycle, we only had 2 equations to work with. Those were the good old days, yeah? We had PV equals RT. And we had the first law. du is delta Q plus delta delta delta. And the thing that we're interested in is, in any given process, how much heat do we have to put in to get out a certain amount of work? So let's look at step 1 to 2. We often model this for an idealized system, which is a frictionless, massless piston. Another modeling element that we use is this concept of reversibility, and step 1 to 2 by definition is isothermal. It's true that work is always equal to force times a change in distance. And in this case, what we're pushing against, the force is pushing against an external pressure. So work is equal to force times an infinitesimal change in volume. Using the idea of reversibility, using the ideal gas law, and using the fact that it's isothermal, from here we could derive that work, in this case, is equal to negative RT, natural log, of the volume of the final state over the initial state. We also use this process to learn that for a perfect gas, there is no change in internal energy when you don't have a change in temperature. And from that, we can also conclude that the heat flow, I want you to answer for yourself whether heat flow is into or out of the system, but heat flow in this case is going to be equal to the negative of what work is equal to. these equations will be true for both isothermal steps, both steps 1 to 2 and steps 3 to 4. For steps 2 to 3, this is again a reversible process, and now it's constant volume. Another word for that is isochoric, which means constant volume. Scooch this over a bit. In this case, it's still true, always true for expansion work. That work is equal to external pressure, the force we're pushing against, times the change in volume. But because it's constant volume, this is 0. So from here, we conclude that the change of the internal energy of the system is going to be equal to the heat flow in or out of the system. And how much heat flows in or out of the system, or what the change in internal energy is for this process here where temperature is changing, is the equivalent of asking how much will you change given some change in temperature. And maybe from your earlier education years, we learned about a quantity called heat capacity, which is a material property that explains to us how much energy I have to put in to get a certain temperature change. In this case, we're going to specify that we're using a constant volume heat capacity, and it's defined as the change in internal energy over the change in temperature at a constant volume. Making some assumptions then, and make sure you can recapitulate these steps. We know that the heat for this process is equal to the change in internal energy, which is CV delta T. This series of 4 steps is called the Stirling Cycle. And it just so happens that Stirling engines are my favorite thermodynamic project, and they're my favorite way to introduce how we might work our way around a cycle, and it's the simplest cycle to solve since we're using only these 2 equations to solve for everything. I guess it's these 2 equations in this definition. So now let's look at a constant pressure process and what that did for us. I'll start again with my PV diagram. And even if we're not talking about an isothermal process, I almost always draw isotherms on just because it helps me visually keep track of when temperature is changing. So here's a constant pressure process from state 1 to state 2. Again, in this model system, we're going to consider it reversible, and the term for constant pressure is isobaric. To calculate the amount of work in or out for this process, I start in the same place I always do. And in this case, because pressure is constant, it's reversible, so this becomes equivalent to the pressure of our system. And then pressure is constant, so I can pull it out of the integral. And I get work is equal to negative P delta V. Let's make that a bigger delta so I can try to be clear about my uppercase and lowercase letters. But now we're a little bit stuck. We don't have a way yet to get from, we know the work, but we don't have a way to get the heat or the internal energy. But we're going to use the idea that because internal energy is a state function, we aren't confined to staying along this path to calculate the change in internal energy between state 1 and 2. I realized in class that the short person favorable path is to first do isothermal expansion to some intermediate state, let's call it A, and then constant volume heating back to state 2. So again, because U is a state function, it doesn't matter whether we get from state 1 to 2 by going along this path, by going along this path we just invented, or any other arbitrary path between state 1 and 2. So for state 1 to A, just like in the Stirling cycle, the change in internal energy for an isothermal process is equal to 0. And so from that, I can conclude that Q is going to be equal to negative W, so it's P delta V. From state A to 2, now I can again, just like the constant volume process in the Stirling cycle, I can use my definition of the constant volume heat capacity to show that delta U is equal to CV delta T for this process. And then in this case, volume doesn't change, and so Q is also going to be equal to CV delta T. So that's Q for the state A to 2, but what about Q for state 1 to 2? Let's start by rewriting the first law. So if I solve the first law for the change in heat, or for the heat flow, I should say, I can say that this is going to integrate out when I integrate this equation out. I'm going to get that Q is equal to delta U now, so U of the second state minus U of the first state. The integral of dW earlier solved to, so it's a minus sign. It solved to negative P delta V, but we have a minus sign, so it's plus P V2 minus V1. Because pressure is constant along this path, I'm going to do a strange thing, which is I'm going to actually, instead of pulling P out and simplifying it, I'm going to specify pressure of the second state and pressure of the first state. So I can rewrite this as U2 minus U1 plus P2V2 minus P1V1. And then I'm just going to rearrange terms. And from here, what it looks like, it's almost as if there's some other state function that identifies how much heat flows in and out of the system. So when this quantity appeared over and over again in derivations, humans decided to give it a new name. They gave it the name enthalpy, and they defined it to be equal to the internal energy plus pressure times volume. And what is so useful about the enthalpy is it gives us the change in heat, or it gives us the heat flow in and out of a system for constant pressure systems. And because we live at constant pressure, we are often trying to calculate constant pressure processes. We also came to define the constant pressure heat capacity as being equal to the change in enthalpy as a function of the change in temperature with constant pressure. So what we'll do in the next new video is define an adiabatic process, and that's going to be the last process that we have to solve before we can do the Carnot cycle, which is going to lead us to be able to calculate engine efficiency.